So back to class, and first schedule note. This week we're going to machine. You've already laser cut and printed, then we're going to mold and cast. For these weeks, the labs provide the materials. Monday's recitation is an important one. We have two impressive people joining to talk about sustainable materials. So where do the materials come that you're using? And in particular, how to source and produce high performance materials from locally available resources. So that'll be the Monday recitation. Moving beyond supply chains outside of your lab to look at sourcing and producing materials. Today's class is an exciting one. This again is one of the more expressive classes. The assignment for this week is to make something big. I've got linked here a dramatic example. This was a colleague who used the machine you'll be using this week to make this house at the Museum of Modern Art in New York. This assignment I'm featuring is, this was homework for this week. This was making this beautiful kayak. Later I'll talk about the composite skin. This goes beyond what you might get done this week. But this was the homework assignment somebody did for this week for Make Something Big. So we're going to cover large format machining. You've been using small milling machines. We're now going to use big ones. So as an example, one example is, this is a business story on a startup that came out of this class project. So David, his girlfriend wanted a standing desk and couldn't find a good one. And so David used a large format milling machine to cut out parts to assemble this desk to make the standing desk. Now, the one, you'll be able to do this. The one detail is this is nicer wood than your lab will provide. This is much more expensive wood, and I'll talk about that. But if you want to source nicer wood, this week you can prototype it. But that's an example of what you can make. Let's see, let's go back to here. This is an open design site for furniture. And these are all examples of the sorts of things we'll be doing this week. Here's another one. So these are the sorts of things, examples of what you can do this week. And beyond that, there's even bigger scales. This is a project using the tools to make emergency shelter. These are a series of projects using the sort of tools you're using to make open house designs. This was a small house project, and probably the biggest house project to come out of a fab lab was this huge one that came from Barcelona. Many people, a lot of time, a lot of work, really challenging, but using all the skills we're going to do this week just on an even bigger scale. Oh, and sorry, I should absolutely, there's a reminder that iFurniture let's see, where's the site for iFurniture? Vanessa, are you there?
Hi, Neil. We are problems with the site.
Okay, but so we'll get to this when we get to startups. You'll meet iFurniture, which is a great example, and I'll add iFurniture for this week. So you're going to be able to do all of that. There's a lot to learn. So the first is the machines. Shaper was started by a former student. This is a router. It's something you move by hand. But instead of just moving it by hand, it's computer controlled. So you do the coarse motion and it does the fine motion. You can't use this to make giant things. Your arms aren't long enough. But that one is unique because all the other machines, you bring your stock to the machine. This one is different because you can bring it to wherever your stock is. Next door to that, this is a version of the other machines we're going to cover are big gantries. This is like the drawing robots we've seen, but instead for cutting in wood. And so it's an interesting hybrid along the way to the bigger machines. The classic machine for this week is the ShopBot. And the founder of this is a good friend on the lab. And so it's a 4-foot by 8-foot by 1-foot work volume with a hefty machining spindle. And depending on the version you get, those are between about $20,000 and $30,000. Ansrud is like that, but $100,000. And the difference is, let's see, Philemon is asking about gantry. Do you mean gantry? Gantry is the thing that moves over the workspace. So the Ansrud compared to the ShopBot is much stiffer. The ShopBot you bolt together and you periodically need to readjust it. The Ansrud is just made rigid at the factory. And so on the scale of a fab lab, the difference doesn't matter. The difference matters in volume production. I wouldn't use a ShopBot, around the clock. This is designed for a higher volume production. Then these next sort of machines is, for example, in the shop at MIT, this is a VMC, a vertical machining center. And so this one can move in 3 axes, but it can also rotate and tilt so you get 2 more axes, so 5 axes, so it can get to any side. And then this is a much faster spindle and a much stiffer machine. So this can do high-speed machining in very hard materials like stainless steel. You can't do on something like a ShopBot. A really interesting machine in my lab is a Zund, and in some of the super labs, this is a large format flatbed cutter. And so you can machine, but you can also, it has heads that can punch or shear or cut or vibrate. And so these are, you can buy 2 fab labs for one of these. It's about a $200,000 machine, but they have all sorts of interesting use cases. And then actually I'll replace that link with this. In the recitation after this one is machine building. And these are all examples of open designs of machines made in, that you can make in fab labs. Jens in Norway in the Felles Verkstedt project has perhaps gotten the furthest in, let's see, he has a in particular, he has a family of machines like the ones we're going to be doing. Let's see, let me find the documentation for this one. So this is a large format machine like you're going to be doing, but this is an open design for it. And he has a whole series of one of these making a child machine that makes another child machine. And so he's using these to make more of these machines. So, but the basis of this week is a machine like a ShopBot. Typically, again, and that's designed around, in the US, plywood sheets that I'll talk about. Typical size is 4-foot by 8-foot, which is the characteristic size of the ShopBot. So you'll need a large format machine. Then you need stock for it. So believe it or not, one of the most interesting materials is cardboard. So you can get heavy duty, thicker cardboard than you're laser cutting. You can cut it with a spindle, but it doesn't really machine well. It really wants a knife. You can use what's called a drag knife, like on the vinyl cutter, on a tool like the ShopBot, but much better is on something like the Zund, a driven knife, where you can control the angle of the knife and you can also vibrate the knife. And with that, you can actually plot furniture right in cardboard that's recycled, renewable, you fold and assemble, that's surprisingly high performance. Foam insulation, like you use in a building, you can machine that easily. The main use for that is to make large molds. And then the focus this week is going to be on wood. So veneer plywood, where you have layers of wood laminated, can make beautiful wood like you saw in David's desk. That's fairly expensive. So that can be, $100, more than $100 for a 4x8 sheet. Medium density fiberboard. This is used, for example, in advertising signs. That's short wood fibers in a glue binder. So compared to veneer plywood, it's cheaper, but it's heavy and it has very poor mechanical properties. If you in tension, the fibers don't really carry the load and you can just shear the binder. And some of these binders can even be hazardous for the gases they outgas. But what's nice about it is it machines easily because it's very homogeneous, and you can get a very smooth surface, which is why it's used, for example, in billboards. MDO is a plywood core that has better structural properties with MDF for a smooth surface. And then we get to OSB, oriented strand board. OSB is kind of literally like the sausage or the hot dog of wood. So in food, sausage or hot dogs are made from what's left over. OSB is little chunks of wood finished after other processes put together. So OSB is the cheapest. Let's see, if we go to in the US, Depot, so a site, and I'll talk more about vendors, lists many different kinds of wood. And so right now, this is $16 for a sheet of OSB. That used to be closer to $10. And then as I scroll through, you can see how the price goes up as you go to higher quality wood. But yeah, about $15 is typical now for a sheet of OSB. Now, OSB has a rough surface, so it's often used for just like boarding up if a window breaks and you want to quickly slap something up. But you can machine it, and then it has a bad reputation because the surface is rough, because it's chunks of wood stuck together. But you can sand OSB, and in particular, you can finish it. And so if you sand it and encapsulate it, you can turn OSB into nice smooth surfaces. And so you can make beautiful things out of OSB. It's considered a crude wood just used for, like, again, boarding up. We use it to start in this class because it's cheap. But it's important to know you can sand it, you can varnish it, you can paint it and seal it. And so you can actually make really nice things out of inexpensive OSB. So that's the typical focus for what we'll be using. HDPE is a plastic that machines easily. And so that was used, for example, in these machines. We'll talk more about that. Lexan or polycarbonate is a really tough plastic. This is used for what's called bulletproof glass. It's shatterproof. You can't laser cut this without a very powerful laser, but it's fairly straightforward to machine. So you can machine polycarbonate. Garolite is an interesting material. It's a composite, but it's not a hazardous composite. So it's like a cotton fiber in a polymer matrix. This is what's used for the substrates in FR1 circuit boards, not FR4, but FR1. And this machines very easily, but has good structural properties. And so this is an example of machine building using garolite to make these machine components. And then you can machine aluminum on a tool like a ShopBot. It's fairly easy to machine. But a nice compromise is highlight is an aluminum cladding layer on a polymer core that makes it even easier to machine and makes it easier to bend. And so an example there is this was an art piece done by some of my students, and using the large flatbed cutter, it was about 5 hours to go from sheet stock to these finished art pieces. And that's done using highlight, where the outside looks like beautiful aluminum, but you machine through into the polymer core that you can use to make folds to bend these shapes. And so that was done with highlight. So those are materials for this week, and likely focus in your labs will be something like OSB. Then for vendors, McMaster Carr is a general purpose vendor in the US. You can buy metal and plastic from them, but anything you buy is much more expensive than buying it directly. Plastics, it's much cheaper to get from a dedicated vendor. This is an example of a US plastic vendor. Metals, again, it's cheaper from a dedicated metals vendor. And then these, again, these are just local to me in the US, but they're typical. This is a wood vendor, and these typically sell into contractors doing things like building houses, and they deal in large volumes. And so they can source the wood you want. But one of the tricks for them is when somebody builds a whole housing development, in that big order, there'll be some wood left over. And so what they consider scrap, you would consider a whole project. And so along with just ordering directly, if you find your local lumber vendors, talk to them, learn about their supplies, and often they'll have things left over from big jobs that they can sell much more cheaply. So these I wouldn't buy from vendors at a distance. I'd look in your neighborhood to find who are your plastic, metal, and wood vendors. Then you're going to do it this week, but these are job shops. So Proto Labs has any of the processes we're talking about, and after you design it this week, you can send it to them. Increasingly, the PCB houses now also do machining. And so the same place you order your PCB, you can send it a design file, and then they can do the machining for you. So there's a number of those. And then there are a number of platforms like this. This is a job shop, but what's different is instead of sending it to a central site, this is a network of about 10,000 job shops. And so you send it to a central site, and then it fans out, and job shops locally do the fulfillment. And in fact, it would be interesting to develop something like this for the Fab network itself. So you can both send jobs elsewhere, but you can do jobs, would be an interesting exercise. So those are important to be aware of for the future if you want to start scaling production of what you make this week. Now, big topic is tooling. So in the inventory, when you made PCBs, about the only choice was, do you use there's a 1/64 inch end mill, there's a tapered end mill, or a V-bit. This is a standard set of tooling when we're setting up a fab lab. And so for large format machining, there are many different choices. So the first distinction is a drill comes down to a point and then has flutes, and it can only go down. It makes holes. A flat end mill has flutes going all the way down, and it's designed to plunge, but primarily to cut on the side. So we're going to be using mills, not drills. Router bits, so an end mill can plunge as long as the length of the mill. Router bits aren't designed to plunge. They have a fixed depth, but they're shaped. And so in particular with router bits, you can make a slot, but you can also make shapes. For example, when you think about molding in a cabinet, router bits only go in 2D, and you can use those to make shapes. The flutes on an end mill are the spirals, and typical numbers are there's 2 flute end mills, and having 2 flutes leaves lots of room to get chips out, but the finish is rougher. A 4 flute end mill has more flutes, which means there's less room to clear chips, but each bite is smaller, and so that can make a smoother surface. And we'll talk about rough versus finish cutting. When you buy an end mill, they're made out of a hard material like carbide. You can spend a little bit more money and get them with a ceramic coating, like titanium nitride. The coatings make them a much harder surface, so the end mill lasts much longer. So typically we always want that. Then there's center cutting and up and down cutting. So if you look at the bottom face of an end mill, so looking up in this direction, one kind, there's a gap in the middle, and the other kind, the flutes meet in the middle. So this kind has room on the bottom that helps it clear chips, but you can't plunge because it doesn't cut there. This kind cuts all the way into the center, which means you can plunge with it, but it's not quite as good at clearing chips. Then if you have an end mill, they typically turn clockwise. So if you have an end mill where the flutes are going like this, that means it's lifting up the chip. So if this is our stock and you come in with that and you lift up, what it's going to be doing is it's going to be trying to pull up the top of your stock, and you might get a rougher finish. There are down cutting end mills that push the chip down. So if you use one of those, it's pushing down, and so you get a cleaner top surface. The problem is there's nowhere for the chips to go. So a common thing you can do is start with a down cut at the top to get a clean top surface, and then finish the rest with an upcut that gives you a clean bottom surface and pulls the chips out. And in fact, you can get combinations of both. So you can get an end mill that meets in the middle of a down cut and an up cut. So if you come in from the side, it's pulling down on the top and it's pulling up on the bottom. And so there's a choice between center cutting, up cut, and down cut for your end mill. And then something we'll see more of in molding and casting. There's a flat bottom end mill. And so if you cut with it on a flat surface, you get a flat surface. There are ball end mills where the bottom is curving with the flutes coming up. And so if you cut in layers, a flat end mill in Z gives you steps, where the ball end mill gives you smoother curves. And so it's common to use a ball end mill for finish cutting. However, when we do full 3-axis machining, which I'll talk about in molding and casting, you can get the same result with a flat end mill. So all of these are choices for the tooling. You'll have a standard suggestion for your lab, but in the space we're going in, there are many, many different kinds of tools. Then comes speeds and feeds. So the machinery handbook is a really handy book you should have in your lab somewhere as a reference. It's a Bible of, let's see, it's a slowly loading site, but it's a Bible of machining wisdom. Speeds and feeds are, you have to decide how fast the spindle turns, how deep you cut, and how fast you cut. So if you think about the looking from above, the end mill turning, if you go slowly, each succeeding pass is making a tiny bite. If you go quickly, each succeeding pass is making a really big bite. If you go too fast, the machine will vibrate, it'll scream, it'll make noise, it'll overheat, and eventually you can break a tool. So that's bad. If you go too slow, you're wasting time. But it's even worse than that. The tool needs to bite to cut in. If you go too slow, it's not even getting a good bite into the material, and it might not even cut effectively. So there's a happy place in between. So the chip load is in each succeeding pass. Let's see. If here's the tool we're machining, and in each succeeding pass, the size of the chip is the feed rate divided by the revolutions per minute times the number of flutes. And in inch units, somewhere between 1 and 10 thousandths of an inch is typical for a good chip load. The cut depth is, if this is the stock and the tool comes through and makes a pass, on the next pass, it's how much deeper you go. And for that, for the cut depth, roughly a good rule of thumb is if this is the diameter of the tool, that's also a good scale for the depth down. So you go down by roughly the diameter of the tool. And then the step over is, if you're just cutting it out, you'll only make one pass. But if you're machining, for example, a pocket, you'll have multiple passes. And so that if you step over like that, looking from below, there'll be a little lip. And so a typical step over is about 50%, is how much you overlap succeeding passes so that you get a smooth surface. So for any machine and for any material, you need to determine the speeds and feeds. And on one side, you're wasting time and being inefficient, and the other side, it turns from you get a rough result because everything's vibrating to there's real safety hazards I'll talk about. And in your shop, there'll be standard speeds and feeds for the materials and machine you're using. So then you likely won't be using lubricants. When you machine, lubricants do two different things. They help lubricate, they help the tool move and cut. The other thing is they help take heat away. You don't need them ever for wood. You can, depending on the process, you can use them on metal. But in fact, when I talk about tool paths, there can be, in some cases, an argument to avoid lubricants for metal cutting in high-speed machining. Let's see, Stephen is asking about the cut length. The answer, Stephen, is the cut depth is only in one pass. So meaning, here's our end mill. And so the first pass will be that deep, the next one will be that deep, but we want to keep going. The total number of passes you can do is the tool length, but any one pass is only by the tool diameter. So separate the cut depth for one pass versus the total depth, which is after many passes. So generally, you don't need to worry about lubricants. Now, it's important to know about abrasive machining. So where do these, end mills can be, and I think are beautiful. So where do they come from? They're typically made by grinding. So these are computerized grinding machines that you use to produce something like an end mill. There's a version of that you can do with abrasive powders. So you can't machine glass, but what you can do is if you take a tool that doesn't even have any flutes, think of like the back of a drill, and you put it in a slurry of an abrasive powder, a very hard material, then when you spin this around, the abrasive powder will grind away and you can actually machine with an abrasive slurry. So that lets you machine hard material. It's kind of like a micro grinding. The one caution about that is you have to be very careful to confine the abrasive slurry, because if it gets into the axes of your machine, it'll grind your bearings and damage the machine. But you can use that to machine hard materials. Now, fixturing is a huge subject. Before, you just used tape or a side clamp for the PCB. A big part of large format is machining is fixturing. So one way to do it is with a vise. And so this, for example, is a machining vise. And unlike, and actually this is not even a particularly expensive one. So $1,000, so a little bench vise can be $10. $1,000 is typical for one of these. Unlike the bench vise, the surfaces are all precision machined and ground to flat surfaces, and everything is perpendicular. So when you clamp something in this, you're perfectly aligned in the coordinates of the machine. So you can use a vise that's limited by the size of it. You can use bar clamps. So these are handy clamps.
I'm listening to.
Konstantin, do you need to mute? Here, I'll mute all, unmute if you want to talk. So with a bar clamp, what you can do is if this is the bed of your machine and then you put your stock on it, you can very quickly just use a bar clamp to hold it from the sides. The problem with that is that holds at the sides. And if you're machining near the bar clamp, that's fine. But if you machine in the middle, and for example, you're doing an upcut, it's trying to lift your stock up and the stock can actually lift away from the bed. So bar clamps are quick and easy. They're good if you're not machining too far from the clamp or if the vertical force isn't large. Screws are surprisingly handy. So here what you do is, if this is the bed of the machine and this is your stock, with a cordless screwdriver, you just put in some screws. And obviously you want to put them where you're not machining. But what those do is they're quick to pop in. And then you're distributing the hold down everywhere, not at the edges. And then you just pop them out at the end. And so that's a common way to do fixturing. There are special nails for machining where you pop these in with a nail gun. And here you don't even need to worry about hitting them. You can machine right through them. Then a machine like the, let's see, Ricardo's asking about, yeah, I'll tell you, I don't know a generic name for that. So on a tool like the Onsrud, it has a vacuum bed. And this is an example of somebody making their own vacuum bed. So you make a plenum, you pull a vacuum and you have a lot of little holes and you just slap your stock down. And so vacuum beds are great because the hold down is everywhere and you don't need to apply anything and take it away. And so these are particularly used in volume production. If you're a job shop, you don't want to spend a lot of time fixturing. You just quickly put your stock on and take it away. These do need maintenance. As you machine, you'll plug the holes. And so you need to periodically clean the vacuum bed. But that's the handiest way to do it. Then there are all sorts of wedges and specialized clamps. If there aren't vertical forces, you can use weights. If it's only a small piece of stock, you can use a bead of, for example, hot melt glue that you chip off. Again, if the forces aren't very large, you can use carpet tape. And finally, when you're doing really complex multi-axis machining, how do you even hold it? Because you need to come in from all sides. And there a technique is, if you're making a metal part, you cast a high temperature metal in a low temperature metal. You then put that whole thing in the work holding, and the low temperature metal holds the high temperature metal. You do all your machining, and then you melt away the low temperature metal, and so you encapsulate. And so most likely you'll be using something like the wood screws for fixturing, or clamps, depending on the bed size. Then in all of these examples, I'm showing doing operations like driving in screws or nails. And when we machine, if this is your stock, you want to cut out your part completely. And so it means we're going to be cutting into something underneath. And so your machine will have a sacrificial layer that you can machine into. It's a bigger job to change these compared to the little milling machines. But periodically what you do is you put in a new sacrificial layer. You run a job where you machine the whole bed. It takes a long time. And what you're doing is you're making the bed flat in the coordinate system of the machine. then you use it, and eventually if you look from above, you'll see the history of every project made on it. And eventually, when there's enough of them, there's not enough of the sacrificial layer left, and you need to replace it. And then squaring is, the Onsrod is just the Onsrod, but the shop bot is bolted together. And over time, everything walks a bit. And so eventually, exaggerating, the bed of the shop bot might not be square. Or if we look at the z-axis, instead of being vertical, the z-axis is slightly tilted. So when you first assemble the machine, you need to square it to get everything perpendicular. And then periodically, you check that, and every few years, you need to re-square the machine on a lower end machine that's bolted together. Machining wood makes a lot of dust. When I get to safety, it can be a safety hazard, but long before that, it's a mess hazard in your lab. And it's also, you don't want to breathe it. So a good rule of thumb is, so in your shop, you'll have a dust collector that looks something like this. If there's a layer of dust away from the machine, like on a computer next to it, that means the dust collection isn't satisfactory. You should be pulling all the dust away. Now, many of the examples I showed at the beginning had flat surfaces, but like we saw in laser cutting, you don't need to do that. So here, this is a flexure. So start with a flat sheet of wood, and then cutting in many beams that let you make it flexible. And then here, this is kerfing, where you don't machine all the way through. So you have a smooth outer surface, but you can curve on the inner surface. You can kind of do this with OSB. This to really do this properly needs better wood. But with those techniques, you can start with a flat machine and a flat stock, and you can lift it up into a curving surface. Steam bending is where you start with wood and you heat it in a steam box. And then after that, it's softened and you can fold it into a shape, and then it'll retain the shape to make curvy wood shapes. And there's special wood to do that, where in plywood, the laminations go in all directions. You can get special wood that aligns the lamination, that makes it easier to bend for smooth curving surfaces. There are all sorts of fasteners, but one of the goals for this week is to not use any of them. Instead, to design it with joints so that in particular, it's reversible. There are all sorts of glues you can use to hold things together. But done right, you can do this week's assignment just with interesting joints. So you don't need fasteners or glue, and also so that it's easy to disassemble as well as reassemble. So this is a wonderful project that characterized joints. And Rico, am I right that this all came from Kamakura?
I think so.
I believe
I think the research was done in a different lab, actually, to tell you the truth.
I see. I'd be interested to know the history, but either Kamakura or one like it, this was a catalog of the construction techniques. This huge range of joints, each solves a problem of how you bring 2 or 3 or more degrees of freedom together, how you carry loads based on the direction, and what you want to be visible and what you want to be hidden. So each of those is a classic Japanese wood joint. So in woodworking, there's huge ranges of just joinery, the types of joints. In laser cutting, I showed a few. It's a much bigger universe. let's see, Vanessa is posting joints for iFurniture. Oh, okay, great. Then there are many strategies. So reciprocal frame is, let's see, Leo is asking about joints other than 90 degrees. I'm sure there are. Anything you can think of is yes, but I don't know in particular, but I'm sure there are. Reciprocal frame is a joinery strategy for making structures that look like these. And here's an article on that. Tensegrity is a really interesting approach where you have strings are good in tension, but not flexion. And so you combine rigid elements that are purely in compression and flexible elements that are purely in tension, and you can make structures like these. And then the Maxwell criterion dates back to James Clerk Maxwell, who's the founder of electromagnetics. And he wrote a beautiful article. And the heart of that is a key lesson for this week. If you make a bookcase and it looks like that, it'll be a terrible bookcase, because if it shears like this, all the segments have the same length. And so nothing prevents it from wobbling. But if you make the same bookcase and you just have a string going in the diagonals, then it can no longer shear because these are handling the tension load. And so the issue is, in a structure, there are degrees of freedom that can move, and there are constraints that can't move. And if you have more degrees of freedom than constraints, you've made a mechanism that can move, which typically you don't want. If you have more constraints than degrees of freedom, you're wasting material. And so typically you want to match the number of constraints with the number of degrees of freedom, so you make a structure that holds together without wobbling. Now we come to toolpaths. So, and this is where you graduate from mods. To make the PCB, you just clicked and mods made a toolpath. Now there are many, many, many more kinds of toolpaths. So when the tool goes by, the kerf is the material that's removed. We've seen before, but now because we're using bigger tools, offsetting is you want the tool not to cut on the line. You need to offset the tool to account for its thickness. Then if you look at here's our tool. It's in a collet that's then in a spindle that's then on a gantry. This might not be mounted vertically. The bearings might be wearing out. The whole thing might not be mounted properly. And so if this is the center of the tool, when you actually run it, it's going to meander a bit, which means the actual diameter that gets cut is larger than the tool. And the difference between that is called the runout. And so the runout depends on the quality of the tool. Now, here's our tool cutting, and it could go in this direction or in that direction. If you go in this direction, the tool cuts in here and exits here. If you go in this direction, the tool cuts in here and exits there. This is good because it's biting in with a good cut and leaving behind the thin cut there. this is bad because you're biting in where it's hard to get started. And you're leaving the clean finish back there. On the other hand, this is bad because the tool's trying to climb over the stock, and so it makes a big outward force. This is good because biting in is pulling it into the stock. So this direction is called climb machining, and it makes larger forces but cleaner cuts. This is called conventional. It makes smaller forces but rougher cuts. So typically you'll use conventional machining to rough things out. You can use climb machining on a finish cut. Now, you're typically going to be just doing 2D machining this week. We'll be doing 3D machining in molds, but this is relevant for both. A rough cut is where you cut in layers because the side of the end mill cuts much more effectively. This is a finish cut with a large step over, and you can see the features. This is a finish cut with a smaller step over in one direction. This is a finish cut with a smaller step over in two directions. And so just cutting out, which is what you need for this week, you'll rough cut. When we make molds, you'll also need to do finish cuts. So then comes, there's all manner of more advanced tool paths, broadly called high-speed machining. So dry machining is without lubrication. And lubrication, the tool keeps getting hot and cold and hot and cold. Instead, you can just let the tool heat up and stay hot. Ramping is the end mill cuts better on the side. So instead of going straight down and then over, you go down at an angle. Adaptive clearing is a funny sounding thing where you go down first and then work your way up using more of the tool. Swarf is when you can tilt using the side of the tool. Rest is you get most of the material with a big tool, you go back with a smaller tool. And trachoidal is a really funny one. In trachoidal, if this is the side of the stock you're machining, instead of going in a straight line, you go in spirals. And the reason you're doing that is this makes a chip that's big at the beginning and small at the end. This makes a chip small at the beginning, big at the end. Trachoidal makes chips that are roughly the same length over the whole chip. And so by going in spirals, you make more uniform chips that's much more efficient. So more advanced CAM software knows how to do that. One-sided machining is you machine from the top, but if you need to do both sides, you need features to register it. So 2D machining is the tool descends, you make the path, and then you rise. 2.5D is you machine in layers, and that's good for rough cutting. 3D machining is you move all three axes at the same time, and we'll be doing that for things like smooth surfaces. And then beyond that, there's 5-axis. Now, again, we'll worry more about cut depth won't be a limitation for this week, but we'll need to worry about that when we do mold making. T-bones we do need for this week. So let's say you're going to machine a slot that's going to fit another part. It's not going to look like that. Because of the diameter of the tool, it's actually going to look like that. And if you try to put something in, it's going to hit that. So instead, what you do is you make something that can look like that, or just a slight variant is it can look like that. So these are called dog bones or T-bones, where you go slightly beyond. And now with these, something can exactly fit in because you've made that extra space. So that's T-boning or dog boning. You have to worry about it now because the parts are bigger. Then if here's your stock, let's say I want to cut that part out. If I haven't put a screw in the middle, when I make my way around it, when I get near the end, the whole part is going to start vibrating and jiggling and I'm going to get a really rough feature at the very end before it pops out. So one of the things you can do from above is, if this is the slot around it, you can put skinny tabs in that hold it in place, and you just pop the tab out at the end. Or you can onion skin, which is, if this is the top, this is the bottom, you machine almost to the bottom, but not quite. And so when you're done, there's this very thin bit here, and then you can easily just cut that out, this onion skin on the bottom. So tabs and onion skidding hold your piece in place. Otherwise, with large format machining, you'll get very rough features where it comes out. Nesting, this is an open source tool for it. You're going to design your parts. You then need to pack them onto your stock. And done well, it uses it efficiently. Done poorly, you're wasting space. So nesting is software. You can do it by hand, but nesting is software to pack your parts to make good use of the stock. Many things can go wrong this week. You can cut with the dimensions wrong. You can have the directions wrong. You can have the speeds and feeds wrong. So one of the first things you should do is just cut air. So that's, you move the tool above where you're going to cut, set the 0 point there, and start your job not touching anything to make sure it makes sense. And often when you start, it'll do something wrong. And then another thing is, before you use up your whole big sheet stock, just make a little test cut. Cut out like a little 1-inch square. Make a little test pattern just to make sure everything is working properly before you risk doing it wrong on the big size. Depending on the software you're using, the more powerful tools can simulate the machining process. And one other suggestion for this week is you can do everything in CAD, but it can be useful to laser cut in cardboard a small version. So if you're going to make a big table, it can be worth the time to laser cut your table in cardboard, and you can discover some things there that you might not see in the CAD before you make the full-size version. So many different CAD options for this week. VCarve is software from ShopBot. Mastercam is a common CAD tool. FreeCAD has a path extension. If you're using SolidWorks, it has its CAM tool. One of the strengths of Fusion is Fusion has probably the best integrated CAD to CAM, where you can do the toolpath and you can simulate in it. Just in mods, you can bring in the design, and there are all the settings you need for the cut depth and the feed rate, and you can make the toolpath there. So you could add to mods. I haven't done it. Mods can do tabs, but not the more advanced toolpaths. But it does do enough just to cut out the path. Yeah, Leo's asking about Meshcam Pro. I'm not familiar with it. Your lab will have one of these workflows to work through the toolpath. Next is, oh, okay, Rico, thank you. So Hiro is one of the pioneers of Fab Labs in Japan. And I didn't realize there was a research paper on the joints. Let me make sure I save a link to that. Let's see, this is the abstract. Where's the article? Ah, okay, beautiful. So, okay, let's see, I'm not sure what site I'm on. So I don't know if I recommend the site I found this on. Oh, this is great. Okay, so that, yeah, this is showing the lineage of where they found that from. Okay, great. Thank you for finding that, Rico.
Looks like that building image you just showed was probably Fab Lab Kamakura.
Good. That was my memory. I wanted to say that it came from Kamakura. In terms of formats, ShopBot has its own internal format, easy but very simple. Far and away, the most common format is G codes. And so most of the machines you'll be using take G codes, and there's a spec. And if you like programming, you can bypass everything I said about the CAM workflows, and you can actually design your own G codes from scratch. If you're going to do it, it's important to run it in a simulator or cut air. And in fact, I'll add a link to the in the software tools like Universal G-code Sender will read the G-code, will simulate what it's going to do for it, and then send it. And Gareth is pointing out there's sites like NC Viewer that'll take your G-code and read it. And so you certainly want to do that before sending it to a machine. Now comes safety. So in the beginning, in project management, I told you mistakes you'd make with Git, with building your sites, and some of you made the mistakes, and it was fine. That they're not hard to correct from. With the laser cutter, we did talk about the issue with fires, but it's not that hard to prevent fires with the laser cutter. This week is different. Large format machining is hazardous. Done properly, it's safe. Done improperly, it's very dangerous. So many years ago, there was a student at Yale. She was using a lathe. Her hair got caught in the lathe and she died. That prompted, for example, at MIT, a really serious re-review of shop access. At MIT, all of our students have to go through a rigorous safety training process to be approved for machining. So many dangers. First one is just splinters from wood. You should wear gloves for that. When the end mills are sharp, the chips can be very sharp. You can many ways to get cut. What's coming off of the machine can be very hot. You can get burnt. Impacts can go flying. And then eventually you can create fires. So this was a, hopefully this will load. This was a lab where they were machining and they had the 0 set wrong between the machine and the toolpath. And so they started machining and it plunged really deeply and then moved pretty quickly. And so the machine was screaming and, you know, there's sort of a dark color. Yeah, not clear why this site isn't loading. So the machine was screaming really unhappy because they were machining way too deeply. They stopped it, they reset it, and they start their job going. And then a little while later, the fire trucks came. And what had happened was they were machining so extremely that the chips turned into glowing embers. They got sucked up into the dust collector. The dust collector started a fire inside. And once that happens, you're kind of doomed because the dust collector is pulling air through this bed of easily ignited chips from the machine. And it's it's a furnace. And so they started a fire in their dust collector. And there's almost no way to fight that. So that was an extreme of machining way out of spec. Tools can break. I had this happen to a student a week ago, just in my lab at MIT. He had an end mill break and it came flying at him and he was protected by his safety glasses. So in turn, you need to wear safety glasses. You cannot be around a large format machine without eye protection. And if you want a reminder, my student last week has his eye because he was wearing his safety glasses. Things can, Rico, the RPM and the feed rate were fine for the depth of cut. The problem is they're cutting way too deep. Things can drop on your toes. You don't want to have open-toed shoes. Your clothes and hair, you can't have long hair that can get caught. You can't wear anything floppy. Those all need to be protected. When you're handling sharp things, you should wear gloves. And it's key to look, listen, and smell. When something is going wrong, you'll see it, you'll hear it, and you might smell it. You need to be aware. Never, ever, ever, ever reach into a powered tool. There are all kinds of sharp, hot things. And so, one of my colleagues, who's one of the gods of machining at MIT, who literally wrote the Bible for it, is missing a finger from that mistake. Each of your machines has an e-stop button. The emergency stop button is what you press to stop it. This sounds obvious, but before you start the machine, make sure you know how to stop it. When something goes wrong, you'll panic. And so it's very important you already have a plan for how to stop the machine. Okay, yeah, this is good, a nice safety picture. And then the last one is you never do this alone. So in grad school, I had a fellow student, we were in the machine shop. He looked over and said, "I'm so bored," and then his finger was cut off. And so fortunately, we were all there and had to rush him to the hospital. He ended up, they couldn't reattach it. He lost his finger, but it was no worse than that. You don't do large format machining alone. You want somebody there for an emergency, but also you want somebody there just to look over and see what you're doing. And the last thing is, you don't do this when you're mad. You don't do it when you're tired. You don't do it when you've had too much coffee. You don't do it when you've had too little coffee. You need to be in a good state. You need to be not rushing. You need to be working at the pace you need to go. You need to be fully present. Unlike the other weeks, this week, the safety risks are real and they're irreversible. Other than that fire, I'm not aware of any personal injuries we've ever had in Fab Academy. In shops I run at MIT, there have been some isolated incidents of student injuries. So safety is absolutely critical for this week. And so each lab will take you through that. Yeah, I won't talk about welding now, but welding can come up when we get to wildcard week. So the group assignment for this week is do your lab safety training. And it may sound obvious, but each of the steps in the safety training is a failure mode. It's something that has either hurt a person or hurt a machine. Then test your run out. Make sure the run out is not excessive. Test alignment. Make sure your machine is squared. Go over the fixturing you're going to be using. Review the speeds and feeds for your machine. And it can be useful. I wouldn't go too far out of spec, but it can be useful to see what it looks like to machine a little too slow or a little too fast. Review the materials you're going to be using. Let's see. Judy, what are you showing?
Hi, it was just like very smart use of material because there's almost no waste. So I'm sort of pretty proud of this design.
Oh, okay. So very clever nesting. And good, a nice example of
nesting.
not even nesting, just designing the whole thing in one go.
It's one piece.
Right. Nice. So go over the materials, and then you'll go through the toolpath setting. And this week, I don't want you to just click print. You really need to understand all of these decisions, because as you progress, as you go to different materials, different machines, you'll need to go back through these settings. Then you'll each get a big piece of stock. I want you to design, mill, and assemble something big. And by big, it means roughly meter scale. So the goal this week is to learn about fixturing, feeds, and speeds. So it needs to be big enough for that. So a laptop stand is maybe right at the edge of big enough. A piece of personal furniture is a good size. Look ahead to your final projects. And then extra credit is see if you can do it without needing fasteners or glue, but just by joining the joint system. And then extra credit is don't have just flat surfaces, but think about how you can have curving surfaces. And at the end of this week, let's see. Ohad, I should add a link to your Fab Lab makeover. Yeah, this was a great example for this week, come to think of it. So there was a sad space that was supposed to be a community center, and they turned it into this beautiful project. And the students got to design their own furniture, then make their own furniture, and it was a sea change for them. It was inspiring, exciting. They all wanted to grow up to be designers and makers. This was a great example. Coming out of this week, you should be inspired to not just buy furniture, but make furniture to customize your lab. Yeah, Enterprise is asking about a treasure chest. That's fine. Again, the meter scale is sort of guidance. The really important thing is this week is about tooling, fixturing, feeds, and speeds. And so you need a project for what you need to do all of those things. And that's the real definition of what's big enough for this week. Okay. So safety, much more important for this week. You're going to be limited by machining time. So get your design work early and get on your machine. Be mindful of the calendar. Time is progressing. We're up to here already. So think about how you can use this week for your final project. And this week you'll be given the material, but Monday you'll learn much more about where these materials come from and how you can start to create your own materials. And with that, this is one of the most expressive weeks. And then we'll come back next week and we'll return to electronics, and you'll learn how to design electronics. So as usual, open time Saturday, rely on that for coaching. It'll be a very interesting recitation Monday for sustainability. And I'll look forward to seeing what you get done next week. Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.
Hasta que la veremos.
Chao.
Adiós.
Adiós, adiós.
Nos vemos.
Chao.
Eh,